Hello guys, welcome to Self-Help Maths Academy. Today we're going to talk about the Gram-Schmidt process. So basically the Gram-Schmidt process is it's a simple algorithm for producing an orthogonal. In turn we'll convert them into orthonormal basis for any non-zero subspace of Rn. So let us understand how exactly it works. Suppose we are given with the basis, say we are given with a basis of vectors, say x1, x2 and so on up to xp for a subspace W of Rn. Okay, then what is the procedure? So the first step is we will start with, let us take our v1 as x1. So here they are given with x1, x2, x3 and so on. So what we will do is we will take our x1 v1 as x1. Then second step is let it be whatever x1 is, but the first step is we will take our v1 as x1. The second step will be v2 is equal to this is x2 minus, okay, x2 dot v1 upon v1 dot v1 into v1. Okay, so if you observe closely, it is the orthogonal projection of x2 onto v1. This quantity. Okay, so here v2 can be found by using x2 because x2 is already we have here. Then v1 we found by the first step. We take the inner product of x2 with v1, and then this same v1, our x1 will be treated as v1 now. v1 dot v1 into v1 will give us v2. Then to find out v3 will be same procedure, x3 minus x3, the projection of x3 onto v1, okay, into v1 minus the projection of x3 onto v2. Okay, so here what we did, or to find out v3, we have already x3 which is given, v1 we found in the first step, v2 we found in the previous step. Okay, so that's how we'll get our v3. So this procedure we continue, and at last you want to find out vp. Okay, that will be your xp minus the projection of xp onto v1 upon v1 dot v1 into v1 minus xp dot v2 upon v2 dot v2 into v2. This we have to continue. If you observe carefully, when I want v3, I have gone up to x3 dot v2. When I want v2, I have gone up to x2 dot v1. So when I want vp, it should be gone up to negative xp dot 1 minus, that is vp minus 1 upon vp minus 1 dot vp minus 1 into vp minus 1. Okay, so this, let me write it nicely, vp minus 1. Okay, so let me change the color to avoid the confusion. So here this is vp minus 1, okay, into vp minus 1. This is our then you have the collection here. If you observe on the left hand side, we have got v1, v2, v3 and so on up to vp. So these v1, v2, v3 and so on up to vp, this collection is an orthogonal. They are orthogonal now. They are orthogonal basis for w. Okay, so in short what we have done is, by the normal basis, these are the normal basis, given normal basis, we have converted them into the orthogonal basis by using the Gram-Schmidt process. So this is the beauty of a Gram-Schmidt algorithm, where the simple basis we convert them into orthogonal. Now this orthogonal basis we can convert them into orthonormal by dividing them by their the norm. Okay, if v1 divided by its norm, you will get the orthonormal. Okay, we can normalize them. Alright, so now let us understand this process with the help of one simple example. So here, let us say, let W is a subspace which is spanned by the vectors x1, x2, where x1 is, they are the normal bases, okay? So 3, 6, 0, 3, 6, 0, and say x2 is given by 1, 2, 2, 1, 2, 2, okay? Construct an orthogonal basis. Sometimes they may ask you orthogonal basis, sometimes they may ask you orthonormal basis by using the v1 v2 of w. Okay, so when they ask you orthogonal basis, we can just do the procedure of Gram-Smith and we can find out. When they ask orthonormal, then extra procedure we have to follow, that is by dividing its norm. So that I will show you with the example. So let me take this one first. So here our x1 is given, x2 is given. So I told you that what is our first step, considering v1 equal to x1, right? So don't stick only on x1 x2, not necessarily that they should give as x1 x2 only. They may give you this as y1 y2, they may give you this as z1 z2, or they may give you with any terminologies, but as long as they're ordinary basis, it's fine. Okay, so just take that v1 is equal to x1. So this is our first step. So what is our v1 equal to x1? This is nothing but we get this as 3, 6, 0. So this is our v1 now. The second step is what? v2. By the definition it says it should be x2 minus x2 dot v1 upon v1 dot v1 into v1. So for to find out this, what all we need, we will calculate them separately. So we need for finding out this, we need x2 dot v1. Okay, so already we have x2, so that is x2 transpose into v1. So this is nothing but your x2 is 1, 2, 2, and your v1 is the same thing. This one is your v1, that is 3, 6, 0. So this gives you 3 plus 12 plus 0, which is equal to 15. Okay, so this is your x2 dot v1. Similarly, find out v1 dot v1. So v1 dot v1 is simply 360 into 360, which is 9 plus 36, which is equal to 45. What we have got is, we have got v1 dot v1, we have got x2 dot v1. Okay, let us substitute them here in this. Now what is our x2? x2 is 1, 2, 2. Okay, so this is 1, 2, 2 minus our x2 dot v1 is 15, v1 dot v1 is 45 times of v1. So what is our v1? v1 is 3, 6, 0. Okay, so this is 15 times of 1, 15 times of 3. This will give us 1, 2, 2. Okay, minus this is 1 over 3 times of 3. This is 1, 6 by 3, which is 2. This is 0. So this will give us 1 minus 1, 0, 2 minus 2, 0, 2 minus 0, that is 2. So this is 0, 0, 2. This is our v2. Okay, we got our v2. Let us find out now, because it has got two vectors. Sorry, this is our v2. So now we have got the required vectors v1 and v2. So v1 and v2, because there are two vectors given, so we will get two orthogonal vectors. So let us check for a cross verification whether this v1 dot v2 are orthogonal or not. So for that, v1 dot v2 we will check. So v1 transpose, just this is for a clarification. Okay, so let us check v1 dot v2. So what is our v1? v1 is 360, and v2 is 0, 0, 2. Okay, so let us find out this. This is 0 plus 0 plus 0, which is equal to 0. So that means the inner product of them, v1 dot v2 is 0, hence they are orthogonal. So therefore whatever we have got the v1 and v2, they are orthogonal basis. Now I'll continue this example a little bit. For example, if in this they ask you to find out the orthonormal, okay, instead of orthogonal, they ask you to find out the orthonormal basis, then how do we convert them into orthonormal? So you know that you know that whatever the v1 we have got, whatever the v2 we have got, so v1 we in this case is 360. Yeah, 360, right? This is 360. Okay, we will find out the norm of v1. So norm of v1, so what is the norm? It is the square root of, I mean, in short, if you know, norm of v square, that we have found, it is square root of v1 dot v1. Okay, so this is equal to what we get, square root of 3 into 3, that is 9, 6 into 6, that is 36. So it is square root of 45. Okay, so square root of 45, you also can write it as 9 into 5 or 3 root 5. Okay, so if I divide our vector, let me consider them the new vector as, say, v1 dash, which is our normalization of vector v1 upon norm of v1. This gives you 1 upon 3 root 5 into 365. Okay, so dividing, what you get, you will be getting here just 1 by root 5. This is 2 by root 5, and this will be root 5 by 3. Okay, so this is your norm orthonormal vector. Okay, but in the same way you can also find out your v2 a dash, which is a orthonormal vector, by using v2 upon norm of v2. What is our norm of v2 here? Same thing, norm of v2 will be square root of v2 dot v2. So you can just find out your v2, that is v2 is 002. Okay, this is equal to 0 plus 0 plus 2 means it is 4. It is just simply 2. Okay, so here this is equal to 1 over 2 into your v2, which is 002, which is again 001. Okay, carefully, if you notice, the length of this vector is simply 1, so they are orthonormal. Now v1 dash and v2 dash are orthonormal vectors. Like this, we can produce the orthogonal vectors by using the Gram-Schmidt process. So let me take another example where we will do this one. For example, they have given you, say, x1 equal to 1 1 1 1, and x2 equal to, say, 0 1 1 1, and x3 equal to, say, 0 0 1 1. Okay, these are the x1 x2 x3, they are clearly the basis. Okay, for a subspace of R4, they are basis of subspace of R4. Okay, now we have to find out the orthogonal basis. Orthogonal basis, say, v1 v2 v3 of R4. Okay, so let us start the procedure. The procedure says, by the Gram-Schmidt process, we know that v1 should be equal to x1. So this is equal to, in this case, 1 1 1 1. This is your v1. Okay, and similarly, let us find out our v2. Let me write it here. So the v2 is equal to x2 minus x2 dot v1 upon v1 dot v1 into v1. So let us find out what all required. So x2 dot v1 we want. This is x2 dot v1, that is, here we can find out 0 1 1 1 into your v1 is 1 1 1. So this is simply 0 plus 1 plus 1 plus 1, which is equal to 3. Okay, similarly, find out your v1 dot v1. v1 dot v1 I'll directly write, so which is equal to 1 plus 1 plus 1 plus 1, which is equal to 4. Okay, so now let me put those values here. This is x2 here is 0 1 1 0 1 1 1 minus x2 dot v1 we got as 3, and v1 dot v1 we got as 4 into v1. So v1 is 1 1 1 1. Okay, so this is simply what you get here is 0 minus 3 by 4, 1 minus 3 by 4, 1 minus 3 by 4, 1 minus 3 by 4. Okay, so the answer is minus 3 by 4, 4 minus 3, that is 1 by 4, 1 by 4 and 1 by 4. This is your v2. Okay, now let us find out v3, because we have got 3 vectors. So therefore this is x3 minus x3 dot v1 upon v1 dot v1 into v1 minus x3 dot v2 upon v2 dot v2 into v2. Okay, so let us find out our required values. We want x3 dot v1, which will be equal to, so here x3 is given as 0 0 1 1 0 0 1 1 and your v1 is given by 1 1 1. So this is simply 1 plus 1, which is equal to 2, and already we found v1 dot v1, so that is 4 we have. So now we want x3 dot v2. x3 dot v2 is 0 0 1 1 and our v2 we got is negative 3 by 4, 1 by 4 and all are 1 by 4. So 1 by 4 and 1 by 4. So this is equal to, so this is simply 1 by 4 plus 1 by 4, because remaining terms we have 0. So this is 2 by 4, which is again 1 by 2. Okay. So now v2 dot v2 also we want. So v2 dot v2 is simply, yeah, this is multiplying this vector with itself. So minus 3 by 4, 1 by 4, 1 by 4, 1 by 4 into minus 3 by 4, 1 by 4, 1 by 4 and 1 by 4. Be careful with the signs and when you're multiplying, guys, because you do mistakes here itself. So this is 9 by 16. So 1 by 16, 1 by 16 and 1 by 16. So 16 is the LCM. So 10, 11, 12. So which is 12 by 16. So this is simply 3 over 4. Okay. So now we have got all the values. So let us substitute them in the is this v3 equation. So what we get, v3 equal to x3. So x3 is 0 0 0 0 1 1 and minus x3 dot v1, that is 2, and v1 dot v1 we all let us substitute all those values into v1, that is 1 1 1 1, x3 dot v2, which is 1 by 2 here, 1 by 2 here, divided by 3 by 4 and into we have got v2, that is minus 3 by 4, 1 by 4, 1 by 4 and 1 by 4. Okay, now let us simplify this. This is equal to 0 0 1 1 and this is 1 over 2. Just let me use the different color, 1 2, and here this one is nothing but like 1 by 2 into 4 by 3. Okay, this one, this entity. So this is 2 times of 1, 2 times of 2, that will be 2 by 3. Okay, so here let me write this as 1 by 2 into 1 1 1 1, and this is here 2 by 3 into minus 3 by 4, 1 by 4, 1 by 4 and 1 by 4. Okay, so let us simplify all this. Now let me write it as one element. This is 0 minus 1 by 2 minus into minus plus 6 by 12. Okay, and then this is 0 minus 1 by 2, this is minus 2 by 3 into this is 2 by 12. Okay, then this is again 1 minus 1 by 2, this is again minus 2 by 12, this is 1 minus 1 by 2 minus 2 by 12. Okay, let us simplify. This is equal to, here 12 is the LCM, so 2 times of 6, so 6 6 minus 6, that is equal to 0. So here we get 0, the first term. Here it is 6 again, so minus 6 minus 2 minus 8 by 12, so minus 8 by 12. This is LCM is 12, so this is 12 and this is 6 and this is 2, so 12 minus 8, that is 4 by 12. Okay, yeah, 4 by 12, and same here, 4 by 12. The final answer is equal to, this is 0 minus 2 times of 4 times of 2, 4 times of 3, 4 times of 1, 4 times of 3, Okay, and 4 times of 1, 4 times of 3. So this is our v3. So whatever we have got now, the collection v1, v2, v3, so these vectors is an orthogonal set. These are our orthogonal set of a non-zero vectors, of a non-zero vectors. Okay, so note that actually here whatever we have got the ordinary basis, we're converting them into the orthogonal basis. That is a very important thing in the orthogonal projection. So let me give you some, so try them guys. Convert them into the orthogonal basis by using the Gram-Schmidt process. Take this as x1, take this as x2, and also try to convert them as orthonormal by dividing them with its norm. Okay, this one, and also comment your answers in the comment box whether you're getting an orthogonality, which how you get, you can write your v1 v2 in the v1 v2 values in the comments. Okay, this is our x2. Let us write -7 -4 1. Okay, try them guys and enjoy your weekend. Okay, till then I think maybe we'll come up with the next concept in the next video. Till then, take care guys. Bye bye.